Well, I'll take them. Okay. Oops. All right, very good. So this is paper 41 from summer 2014. We're looking at Cambridge International Exams Chemistry, A2. So we're going to run through the paper now, and the things that are really obvious, like writing a definition or looking up something in a data book or something like that, we're just going to skip those and try and spend time working on our understanding rather than just filling in things that we know we can look up in a book. All right, very good. So let's get started. Okay, so these first two, both the melting point and the density of iron are greater than calcium. And then you have to explain why you made that decision. And what you want to work on here is talking about ionic radius. Okay, so they might penalize you if you talked about atomic radius, because in the, the metal, you've got metal cations surrounded by delocalized electrons. And so you're talking about the ionic radius rather than the atomic radius. And so the ionic radius of iron is smaller than that of calcium. And that means not only is it a smaller ionic radius, but there's a greater charge density in the nucleus. And the combination of that increase in charge in the nucleus and the smaller ionic radius gives you this greater positive charge density, which is more strongly attracted to the delocalized electrons. And that means that iron has a higher melting point than calcium. And for density, you've got to catch two things there. One is that the relative atomic mass of iron is greater than the relative atomic mass of calcium. And so all the mass of an atom is right in the nucleus. And so you end up with just a smaller volume because you've got a smaller ionic radius, and you've got more mass in that volume as well. And those two factors, a smaller volume and a greater mass, give you the greater density for iron compared to calcium. All right, moving on then. So coming to these cell diagrams here, and they don't sort of specify it in your syllabus, but there is a convention about what goes on the left-hand side and what goes on the right-hand side. And actually in the mark scheme, they don't bother about that too much. But as we go through this, we'll stick to the right convention. Okay, so you've got to kind of fill in the blanks there. You know that you're missing the, there's my pen up here. You're missing, this is a high resistance voltmeter you've got up there. Okay, you just get that from the book. And then you've got your salt bridge connecting the two solutions there. And we'll explain this later on, but on this side, we've got an iron metal over here. And on this side, we've got the copper metal. And then in solution, you've got the iron 2+, and in solution over here, you've got copper 2+. Sometimes in these questions, they ask you about other standard conditions. They haven't done it here, but you need to know that these standard electrode potentials are taken at 298 Kelvin and 1 atmosphere, which is 10 to the 5 pascals. So sometimes they'll ask you about standard conditions. They're not doing that here. So we've just had to fill in there, haven't we, what A, B, C, and D are. We've got the metals and we've got the ions in solution. Okay, so I'm not actually filling in all the answers as we go, but I'm just kind of talking them through. So I mean, some of these easier things we can just talk through. Okay, so they've asked at this point to calculate the cell potential, and they've just given you one line for that. Seems a bit mean on space to do that. And there's lots of different ways that people do this. I'll just show you the way that I use, and I'm just going to use this bit of space that I've got up here. Okay, so we've talked about the answers there. But if you look up in the data book, then you've got a couple of these equilibria, haven't you? So you've got you've got Fe2 plus 2 electrons, and that's in equilibrium with iron metal. Yeah, and you've got Cu2 plus, and that's in equilibrium with copper metal. And in the electrochemical series, these are always written as reductions. Okay, so you should have in your mind as well the mnemonic. Whoops. Did Tom tell you I'm not very good with this pen? Okay, so I'm trying to write here. There's, can you see that? Oil rig. You come across that before? So oil rig is just a little thing to help you remember that O, oxidation is loss of electrons, R, reduction is gain of electrons, okay? And you can see the way that these equilibria are written, they're written as gain of electrons, which is reduction. And you get a standard electrode potential for each of those. And for this one, it is 0.44 volts. And for this one, it is plus 0.34 volts. Now, you probably see lots of different ways in the books of trying to work this out, but I'll just tell you the way that I use. And that is to remember that you're looking at electrodes here, aren't you, in the cell? And so if you look at these two, you have to think, well, which one is the most positive electrode? And the most positive electrode, that's the one that electrons are going to go to, yes? And the most negative electrode, that's the one the electrons are going to leave, all right? So out of these two, the electrons are going to be traveling to copper, and they're going to be leaving the iron, which must mean that this one is the reduction because it's gaining electrons, and we're going to have to swap this one around because that one's losing electrons. It's the negative electrode. Electrons are going to be lost from there. So I'm swapping that around to look like this. And because I've swapped it around, then I have to change the sign of the standard electrode potential as well. And that is the oxidation, all right? So, and once you've worked out which one is the reduction, that one is reduction, it's gaining electrons, it's the most positive. This is the oxidation, it's losing electrons, it's the most negative, so that's loss of electrons. So I've got those two the right way around now. Copper is gaining electrons, iron is losing electrons. And so then I can add those two together, and I've got copper 2 plus iron is going to copper plus iron. And then I can just add the two standard electrode potentials together as well, and that becomes 0.78 volts, which is the number that's meant to go in there. Yes? Okay. And just as a good habit, you should be putting a positive sign in front of anything that's positive rather than leaving it to be implicit. All right, good. So, but you may have other ways of trying to work out cell potentials, but for me, I just try and remember that I'm working with electrodes. The positive electrode will attract electrons. The negative electrode is going to be losing electrons. That's the easiest way for me to remember that. Okay, so now you've got to work on a little bit of Lucia Talias principle. We've put, if you remember in the diagram, we've actually got these the correct way around according to the standard for working out which is on the left and which is on the right. So for us, we've got C and A is the iron 2 plus equilibrium. So for this one, we've got, where's my pen? We've got This is the standard electrode potential that we looked up in the data. Sorry about my writing, guys. And that was negative, wasn't it? That was negative 0.44 volts. And the question is saying, well, if I increase the concentration of this, well, what's going to happen? If I increase the concentration of this, then the position of equilibrium is going to be shifting this way, isn't it? All right? And that means that if you look at that equilibrium, then I will have less electrons because the position of equilibrium is shifted to the right. If I have less electrons, this is going to be less negative. And if that's less negative, then we end up with a cell potential which is decreased. There we go. So the cell potential is going to be decreased. Good. All right, so you're coming down now to some work on a redox titration. And this is a little bit tricky because they're getting you to imagine that you're in a lab doing this experiment. You're trying to think, well, what would I actually see? They don't tell you very much. And the clue is that in your flask, you've got some quite dilute iron solution. And that would be, if anything, it would be pale green. And it might be so dilute that to all intents and purposes, it would appear colorless. Okay, so that's in the flask. And then in the burette that you're running in, it says, we're doing a titration here, so we're trying to reach the end point. So in the burette is this manganate solution. And the trick is that you need to know that manganate is deep purple. That's the color of the manganate. And so if you imagine you're just running in this deep purple color, and as soon as it hits the flask, it reacts. So the deep purple color disappears. You're running in deep purple, you reacted a bit, and the deep purple color disappears. And you want to know, well, when I've completely used up all the iron, then the next drop of strong deep purple color that I add isn't going to disappear anymore. There's nothing in there for it to react. And so you get the deep purple color that you're adding added to this flask, which is mainly colorless. And so your flask stays a kind of light purple pink color. So the reason you're seeing that endpoint is because you're running in this deep purple colored manganate. And when you've just added a slight excess of that, then you get a kind of pale purple or a kind of pink color at the end of the titration. So the trick there was to remember the titrations that you might have done in the lab, and that this manganate 7 that you're running in from the burette is a deep purple color, and you can just see the end point of that when it's added to the solution, and the solution turns a sort of very pale color. All right. Okay, we've got some nice calculations to do now. It's, pretty easy marks here. So they've given us this equation, haven't they, of 5. I hope you can see my writing there. And you've got the manganate that you're running in. You've got some acid in there as well. And we've got a 5-to-1 stoichiometry between the iron and the manganate. And that's going to Fe3+ over here, and the manganese 2, and some water. So when I'm working things out like this, I tend to do the volumes that I'm using. So what was the volume? We had 18.1 there, didn't we? Centimeters cubed. And then another row for concentrations. So another concentration there they gave us was 0.02. And so then I can work out the amount, the number of moles, and that's 3.62 times 10 to the minus 4. And if I kind of keep myself lined up here, then I don't get lost in the calculation. And the only thing you've got to watch there, of course, is that your concentration is in moles per decimeter cubed, and your volume is in centimeters cubed. So you've got to change your volume from centimeters cubed to decimeter cubed before you start working out the amount, the number of moles. So you've got to divide 18.1 divided by 1,000 before you can use it to calculate the number of moles. So that's the number of moles of manganate, and it's very easy at that point to say, well, if I've got that number of moles of manganate, I've got 5 times as many moles of iron. And so we've got, just multiply that by 5, and you get 1.81 times 10 to the minus 3. I think that's a pretty easy mark there. All right. Okay, well, and again, I think more easy marks again. So here we are. Okay, so we calculated up here the amount, the number of moles, and so we just have to work out the mass here. And to work out the mass, you multiply the number of moles, or the amount, times the molar mass. And the molar mass, you can look up in the periodic table in the data book that they gave you. The number of moles is 1.81. We worked that out, times 10 to the minus 3. And the molar mass for iron that you look up is 55.8 grams per mole. And that is in moles. Okay, so moles times grams per mole, and you end up with a mass of iron, which is 1.01 times 10 to the minus 1 grams. Okay, we've got the mass of iron. All right, so, and then this next one down here, again, we've worked out the number of moles up here, and it told us to begin with that we actually had 500 milligrams of the complex. And so we've got to work out the molar mass of the complex. And that just means we've got to rearrange this equation here, doesn't it? So we can make the molar mass the subject of the equation. Okay, so we make molar mass the subject of the equation. The molar mass is equal to the mass divided by the number of moles. So you need to know that milligrams, of course, we've got to convert that to grams because molar mass is in units of grams per mole. So 500 milligrams is the same as 0.5 grams, and we're dividing it by the number of moles, which is what we calculated up there. Got 1.81 times 10 to the minus 3. That's in units of moles, and that gives us an answer of 276.2, and you can see the units here are grams per mole. So molar mass, grams per mole. That was 276.2. I missed writing that there. Good. So that was, I think that's some easy questions there. You're just having to use your relationship between amount, molar mass, and mass, and you happen to use your relationship between volume, concentration, and amount up there. Okay, so this is the kind of question we're going to skip. You could look up the meaning of complex and the meaning of ligand in your textbooks. I think that'll kind of come out as we go through this question. Something gone weird there. Why can't I scroll? Okay, good. Okay, so then you've got to draw the shapes of these two complexes. You can see the first one has got 6 water ligands. The second one has got 4 chloride ligands. Pretty easy stuff again. So you've just got to draw the central metal ion, and then it's surrounded by 4 ligands. And the only trick with these is to make sure that the oxygen, which is donating the lone pair of electrons, that's forming the coordinate bond or the dative bond, is the one that you draw the line to. If you drew the line to the H2, that would be wrong. Do you understand what I mean? So I'm drawing there the line to the oxygen. And it's okay to write water as OH2 rather than H2O. It doesn't matter, as long as you show that the line is going to the oxygen, not the hydrogen. All right, and then you've got this sort of wedge shape that you use to show what's in front of you. So you've got another oxygen there. I'm going to do it as O. I've got to have the lone pair of electrons that are forming the bond from the oxygen, and then there's one going out the back of the paper as well. Same here. And now I can write H2O. can put it there. And there's one going out of the back of the paper as well. So just make sure that you're showing where the lone pair of electrons are coming. And don't forget, you've got to put brackets around that and say, excuse me, brackets, sorry, you've got the 2+ charge overall. Yes? Okay. So that's a few tips and tricks for drawing the octahedral shape. And then for this one, again, you've got copper in the middle. This time it's going to be tetrahedral. So you've got chloride ion up there, chloride ion down there. You've got one going out of the back of the paper, and you've got one coming out of the front of the paper. You can probably do much better diagrams than me because you're writing on a piece of paper rather than using this this pen. And that, put the square brackets around it again, and you've got this time 2 negative, haven't you? So the shape there, octahedral, shape there, tetrahedral. I think tetrahedral. Okay, good. I think quite easy marks for you there. Now, platinum is a bit unusual in that it doesn't form the tetrahedral complexes. It forms square planar complexes. Tells you that in the question. And you've got to show the 2 isomers here. So you've got to have platinum as your central metal ion for both of these. And for square planar, you've got 2 behind the paper. So we could have chlorine there, and 2 in front of the paper. In fact, what I should do is, just to be what I've been telling you, is, what happened there? You understand what I'm doing? Okay, I'm going to write ammonia as H3N, a little bit like we wrote water as OH2. You know, it's kind of back to front, isn't it? Just to show that it's the nitrogen that's denoting the lone pair of electrons, and there's no bond coming from the hydrogen. But you can see here, I've got the 2 ammonia ligands coming out of the paper, and the 2 chloride ligands coming up the back of the paper. So you could swap that around, of course, and you could have chloride there, and you could have an ammonia ligand there, and you could have the ammonia ligand there, and the chloride ligand here. And those 2 are proper isomers. And you can see they've got different arrangements in space. The 2 chloride ligands there are adjacent, whereas here they're opposite. The ammonia ligands are adjacent, here they're opposite. So that type of isomerism is geometric. It's a type of stereoisomerism, isn't it? There's 2 types of stereoisomerism, optical isomerism and geometric. This is a type of geometric isomerism. Okay, so, well, these pretty easy to look up. You need to have 3D9 there, and you need to have 3D10 there. So you can just look up the electron configuration of copper and then take off 2 electrons for copper 2+, or take off 1 electron for copper 1+. And then you've got to do a little bit of explanation for why these ones are coloured. They're typically blue. And these ones aren't coloured. They just appear white. And you've got to explain that. So again, they haven't given us very much room to do that. I'll just talk around it a little bit. But you know that there are 5 d orbitals. And 3 of those d orbitals are lined up with x, y, and z axes. And 2 of those atomic orbitals are in between the axes. Okay? And what happens is that when you have an octahedral complex, you've got six ligands, then these d orbitals get much more, experience much more repulsion okay. These d orbitals experience much more repulsion from the lone pair of electrons that are being donated by the ligand than these do here, because they're not affected as much because they're not exactly on the x, y, and z axes. And so what happens is that 3 of the d orbitals get pushed to a slightly higher energy than the other 2 d orbitals. And so you get a splitting of d orbitals. And the theory about that is called crystal field theory. Okay? It means that as the ligands bind to the copper, 3 of the d orbitals get raised in energy compared to the 2 which aren't raised. And that means that it's possible for an electron to be promoted from a lower to a higher orbital. Because you can see up here, with copper 2+, there's actually a space in one of the d orbitals. If you were writing it out, 1, 2, 3, 4, 5, you'd end up, well, those d orbitals are all filled. 1, 2, 3, 4. So I've drawn one too many, haven't I? Let me draw that again. There's 5 d orbitals. I'll make it a bit bigger. 1, 2, 3, 4, and 5 at the end. And they're all filled except one, which has got a space in it. All right? And so when they become split like this, you can have those at the bottom filled. And these are 2 of these 3 are filled, and one of them is half filled. And that means it's possible for an electron here to be promoted from a lower energy state to a higher energy state, because there's an empty orbital up there. And so we've got the crystal field theory, we've got the split of the d orbitals, we've got one empty, sorry, half empty, isn't it? Half empty d orbital, and electron can be promoted. And what happens as it's promoted is that it absorbs a photon of a particular color of light, and that means that some of the light of a particular frequency is absorbed, leaving the other frequencies that you see. So I think, like, how many marks was this? Have a look. Photon absorbed. Just trying to see if I've got all the right points down there. So I think you've got the d orbitals are split by crystal field theory. You've got one half empty d orbital, an electron can be promoted, and a photon is absorbed. I think that's probably a pretty full answer that you've got there. Well, for copper 1 salts, same kind of things going on, but of course with copper 1, it's got 5d orbitals, but they're all full, aren't they? And so even if those orbitals are split, 3 up, 2 down, even if they are split, you can't promote an electron from a lower energy level to a higher energy level because there isn't a half-filled d orbital ready to be filled. So no empty or half-empty d orbitals. So a total of 5 marks for that question. I think most of the marks went up here. You've got more lines, haven't you? Looks like we had 4 points there, and here we're just getting an extra 1 point that there's no empty or half-empty d orbitals for the electron to be promoted. That's our 5 points. Still continuing about copper, and we've got some values in the table there, and we're just going to, we want to know, don't we, the enthalpy change for this reaction. So the easiest way to do that is to just draw a little cycle. Those are all their elements in their standard states, and that arrow would be the standard enthalpy of formation of copper nitrate, wouldn't it? And then that going there would be the standard enthalpy of formation of copper oxide. And that one going to there is going to be the standard enthalpy of formation of nitrogen dioxide. And you can actually see we're making 2 molecules or 2 moles of nitrogen dioxide. So we're going to have twice the enthalpy of formation of nitrogen oxide because we're making 2 moles of it. So you've got a little cycle here, and you've got one unknown, which is the thing that you're trying to find there. And so you could say, well, according to Hess's law, if you're going from A to B, then there's 2 ways to get there. You could go that way, or you could just go that way, couldn't you? All right, so, sorry, that's going A to B was that. Okay, we're going either in 2 steps or in 1 step. Hess's law. Now, if we went in 2 steps, that would be, what would it be? It would be the enthalpy of formation of the copper nitrate. That's the first step there, isn't it? And that's going to be 1. And that's the second step there, plus the enthalpy that we're trying to find out. And those 2 steps, 1 and 2, are the same as that step over there. And that step over there was the enthalpy of formation of copper oxide, and that one, the enthalpy of formation of nitrogen dioxide. But remember, we had to multiply that by 2. And so you've just got to look at the little Hess's law cycle there and work out, well, that's 2 steps, or that's 1 step, add all those together, and you work out, just have to rearrange so that the enthalpy for the reaction becomes the subject of the equation. And then you put in the numbers, and you're going to end up with 146 kilojoules per mole. And make sure that you put in the positive sign as well, because they sometimes might knock off a mark if you don't include the positive or the negative sign. And you can probably guess what's coming up in these kind of questions. Well, you've just calculated a positive enthalpy for the reaction. That's endothermic, isn't it? And so you're probably thinking ahead here and thinking, well, you've calculated an endothermic reaction. They're going to start asking you some questions about reactions that are endothermic. And that's exactly what they do coming down here. There's it. All right, so there's another, okay, so there's another one here. All right, so exactly the same thing again, I think. You've got to draw a little cycle. And here, you're making copper oxide, aren't you? But you're making 2 moles of it. So that's 2 times the enthalpy of formation of copper oxide. And over here, you're making this copper 1 oxide, aren't you? So you've got the enthalpy of formation of copper 2 oxide. All right, but there's only 1 mole of that, so that gets multiplied by 1. We just leave it as it is, and that's multiplied by 2. And again, Hess's law, it doesn't matter which way you go round, as long as you go from A to B. A is here, B is over there. So we could do 1 step, 2 step, or we could just go this directly in 1 step there. So if we're going around this way, and we're trying to calculate that value there, aren't we? So going around 1, 2, that is 2 times the enthalpy of formation of copper oxide, plus the thing that we're trying to work out. That's going that way around, or you could go straight there, and that's the enthalpy of formation of that. And that's the thing that we're trying to find out. So you've got to rearrange that equation. And then subtract that value from both sides. So minus 2 times enthalpy of formation of copper oxide. You do all that, and again, you're going to end up with, sorry, I got that wrong, didn't I? So that one's 146. I'm copying from some notes here. And that one, my mistake, you work that one out as still endothermic, 220, sorry, still getting wrong, 212 kilojoules per mole, but still exothermic. Same for this one. Okay, so good. We've got 2 endothermic values there. And then you've just got to apply a little bit of Lucia Talias principle there. And they're saying, well, we want more of that. So we want to take the equilibrium and shift the equilibrium to the right-hand side, or have more product. That's our equilibrium. And to get more product, then if you increase the temperature, because Lucia Talias principle says the system at equilibrium will shift to minimize the change that's made upon it. So an endothermic process absorbs energy, and if you add heat energy by raising the temperature, then the system will move to try and minimize that change, and so it'll move to create more product, or the position of equilibrium will shift to the right-hand side to try and absorb the additional heat that's been added by raising the temperature. So, so the temperature would increase, and that will give us more product, which is the copper 1 oxide that you're trying to create there. Okay, some organic molecules that you haven't seen before, probably. And you've got a reaction here where you are breaking a bond. Okay, so that's an amide bond, isn't it? And it's being broken. And the type of reaction that breaks that bond is hydrolysis. Okay, lysis means breaking, hydro is water, and you're adding water across here. So reagents that you can use for that, you can use dilute hydrochloric acid, and you're going to warm that up, so you need to heat it. And that's a hydrolysis of an amide bond. Okay, so it's now talking about looking at the diagrams and trying to work out the number of stereoisomers. And if you look at them, the two types of stereoisomers you can get are either geometric isomers, we saw those a little bit early on, or optical. Now the optical isomers, you need a chiral carbon, a carbon with 4 different things added around it, 4 different bonds, 4 different groups around it. There's no optical isomers in there, but there are some possibilities for geometric isomers because you've got these double bonds which don't allow rotation around the double bond. And the one they gave you, I mean, normally one they gave you here is you normally draw that as a double bond like that. They've drawn the skeletal formula for you, but normally you'd be drawing something like that. And so you've got trans, haven't you? That's a trans, and this one is a trans. Or if you're using the EZ nomenclature, that is EE. All right. So you've got 2 types of you've got these 2 double bonds here. You can get trans, and so the number of combinations would be where you could have cis. That would be one combination. Trans, that's the other one they've given you. And then you could have cis, trans, or you could have trans, cis. Those are the 4 possible combinations that you could have. And it's a bit awkward to see them in the way that they've drawn the skeletal formula here. But if you draw it out in the much more kind of familiar way of drawing double bonds, there's the double bond, carbon at both ends, and then you've got the groups on either side of those carbons. Then you can see that you've got 2 trans bonds there, and the possibilities are you've got 4 different stereoisomers. You've got cis, you've got trans, which is one that they gave you. You've got cis, trans, and then you've got trans, cis. 4 possibilities. You don't have to list them, but that's what they are. And you've just got to choose one of those to draw. And for me, well, they've given us trans, haven't they? And to stop myself getting mixed up, the easiest one for me to draw is cis, because I might get mixed up when I'm drawing these. And so cis is going to be a double bond like that, isn't it? And so you've then got to draw, what is it? You've got to draw the skeletal formula where you've got the cis double bond. And so if you're drawing that out, you're going to get this part over here of the molecule. And you can do better drawings than me because I'm not very good with a pen. You've got your arene in the middle there. And then I would draw, there's my first double bond, and there's my second. And it's absolutely fine to draw it like that. And then you've got a carboxylic acid, haven't you, at the end? I think. What's at the end? Yes, it's an acid. And that's cis as well. Okay, so I found it easier to do the cis rather than to do the cis trans and the trans cis. But you could have any of those 3 other combinations compared to the one that they've already given you. Good. Okay, so this is something that always seems to come up in these CIE exams, and there's no other exam syllabus that does this, so they seem to like using it quite a lot. And that's they're saying that when you've got potassium manganate 7, you need to know that's an oxidizing agent. And when you've got it hot and it's concentrated, that's going to be doing a lot of oxidation. And the thing that you need to know is that when you have hot concentrated, First of all, if you've got a double bond, the first step with the, if that's the double bond, the first step is that you make a diol. You'd actually do that with dilute. But because they've got concentrated, it proceeds to a further step. And so what happens is that bond gets broken and the alcohol group in the diol gets oxidized, and you end up with two carbonyl compounds. Okay, so whenever you get to one of these double bonds here, when it's oxidized with hot concentrated manganate, then first of all you get the diol, and then it's further oxidized to give a carbonyl compound. And then the thing that they like to do is that if a carbonyl compound is also an aldehyde, you can see here, that one might be a ketone. An ketone cannot be further oxidized, but an aldehyde can. So further oxidation. And an aldehyde, when it's oxidized, goes to a carboxylic acid. So what's happening with this hot concentrated manganate 7 is you're rattling through these three oxidations. First of all, a diol, then a carbonyl, and if the carbonyl is an aldehyde, then the aldehyde will become oxidized to a carboxylic acid. So you've got to apply that kind of thinking to the molecule that was over here. So you're going to end up with a carbonyl compound there and a carbonyl compound there. So you can end up with this. Oops. Why is that not? Okay, good. Got it. Rid of that. So you're going to end up with that. And then you've got this aryl group here, this arene. And then you're going to get that from that part of the molecule there. And then you're going to get from that other part of the molecule there, from that part there. And the trick in these kind of questions is to be careful that you don't finish too early, because you've been through the first stage of creating a diol, and then you've been through the second stage, which is creating these carbonyl groups. And then you've got to spot that the carbonyl group that you created, is it an aldehyde or a ketone? If it's a ketone, nothing more happens. If it's an aldehyde, which in this case, it actually was for both of them, they'll do further oxidation, and the aldehydes will be oxidized further to carboxylic acids. So those become further oxidized to give you a carboxylic acid there and a carboxylic acid there. And so the two, I think they ask you the structures that are going to be formed are going to be a carboxylic acid created from that fragment and a carboxylic acid created from that fragment, because they both rattle through this multiple steps of oxidation, first to the diol, then to the carbonyl, and if the carbonyl is an aldehyde, it's further oxidized to a carboxylic acid. Okay, good. So that was, I think that's very, very specific to Cambridge International exams. They seem to ask that one quite a lot. Into some easier work now, looking at the ionic product for water. You've just got to remember that. I shouldn't be writing this, you should just know it. And then you've got to work out a pH based on your knowledge of the ionic product of water and the concentration of sodium hydroxide. And so you're just going to rearrange, aren't you, so that the hydrogen ion concentration is the subject of the equation. So that is the ionic product of water divided by the concentration of the hydroxide ions. And when you work that out, then you get a concentration of hydrogen ions from that of tiny concentration actually, which is what you'd expect. And then you need to know as well that the pH, of course, is, you just punch some numbers into a calculator, is minus the logarithm of the hydrogen ion concentration. So you punch into a calculator the logarithm of the hydrogen ion concentration, which is what we worked out there. You'll get a negative value for it, and you just times it by a negative value to give yourself a positive value, and you end up with a pH of equal to 13 in the calculator, something like that. And pH values are normally expressed to one decimal place, so you'd express that as 13.2 is the pH. Good. And then you're coming down now to this compound, which you probably haven't seen before. And because you know that they've already started talking about acids and bases, you're already alerted that they're probably going to start asking some more questions about acids and bases. And this is a amine. It just happens to be cyclic. There, you've got the carbon chain going around. And it's actually, isn't it, it's a secondary amine. And you know that amines have a lone pair of electrons on them. And that is what makes amines basic. So this is just, actually, it's just a secondary amine, just drawn a bit like this. And you've got to calculate, actually, that the solution is okay. All right. So this is, I'm just looking at the question paper again. So you've got a 1.5 mole per decimeter cube solution of this secondary amine, which is a weak base, and you're comparing it, aren't you, to this, which is a 0.15 mole per decimeter cube solution of a strong base. Sodium hydroxide is a strong base. And so we'd expect this to have a higher pH and this to have a lower pH, because this secondary amine is a weak base compared to the sodium hydroxide. So, weaker base. The secondary amine is a weaker base compared to hydroxide ions. Good. And then you've got to compare, haven't you, ammonia, which also has a lone pair of electrons, so it's a weak base, and you've got to compare it to the compound in the question, and we've already said that that's a secondary amine. And your question is, well, which one actually is a stronger base? Is it ammonia or is it this? And what you need to spot is that because this is, these are all CH2 groups going around here, or CH3 groups, then you've got what's called electron donating, or a better word for that is a positive inductive effect, which means you have greater electron density on the nitrogen. So this nitrogen has a greater electron density than this nitrogen here, even though they've both got the same number of lone pairs, one lone pair each, because these groups here donate electrons onto the nitrogen, and that's called a positive inductive effect. There's a greater electron density on the nitrogen, so this nitrogen here is a better proton acceptor, and so it's a stronger, you have to excuse my writing, stronger base. It's the electrons are donated, The nitrogen has a slightly more negative charge. It's a better proton acceptor, and therefore it's a stronger base. So we expect piperidine to be stronger than ammonia. So, and we've explained that. Piperidine is a stronger base than ammonia. Good. I hope you can understand my bad writing, because I'm talking it through, but I don't find the pen that easy to use, so the writing ends up quite bad. Okay, all right, so now we've got, we've been talking about acids and bases, strong acids, weak bases, strong bases. Looks like we're going to get into acid-base titrations a bit later on. And here we go then. So we've got a solution of piperidine, we're adding hydrochloric acid to it. I find it easier to draw what I'm talking about, so I know what I'm doing. So that's the piperidine, that's the hydrochloric acid. And when they react together, then you get, I'll try and draw that again. That's a hydrochloric acid. And there's a hydrogen atom off there, isn't there, as well? Because it's a secondary amine. And when it reacts with hydrochloric acid, then you get that forming there. Okay, that's the reaction between piperidine and hydrochloric acid. And so it tells us that we've got a volume to begin with. We had 10 centimeters cubed of that, and we had 20 centimeters cubed of that. We had concentrations. You see I'm lining everything up again here as I did before. We had the concentration here was 0.15. Over here, the concentration was 0.1. And so that we can then work out the amounts. And the amounts work out at, if you do the calculation, 1.5 times 10 to the minus 3. And over here, the amounts work out as 2 times 10 to the minus 3. And you can see when you write out the equations I've done here, and then work out the reacting amounts, that the reaction stoichiometry is 1-to-1. 1 molecule of hydrogen chloride will react with 1 mole of piperidine. And so you can see that the hydrogen chloride is in excess, just there. And you've got to calculate the amount that is left over at the end. Well, if the hydrogen chloride was in excess, then you can see that the excess is that number there minus that number there, and you work out with an excess of this number of moles of hydrochloric acid. Now, if you've got that number of moles of hydrochloric acid, and you know the volume, because you've got 20 centimeters cubed there, and you mixed it with 10 centimeters cubed there, then you can work out the pH again, because you know that pH is equal to minus the logarithm of the hydrogen ion concentration. So your concentration is the amount, or the number of moles, which was 5 times 10 to the minus 4 moles. And your volume, well, you know your volume is 20 plus 30, but that's in centimeters cubed. So you've got to convert your centimeters cubed to decimeters cubed. So you've got 0.3 decimeters cubed. And then you divide those two, and you end up with a concentration of 0. I think you end up with, I'm looking at my notes, you end up with that concentration of hydrogen ions. I think you probably had 0.6 recurring there. And then you just plug that into your calculator as the logarithm of the hydrogen ion concentration. That was our hydrogen ion concentration. And then you just multiply it by a negative, and you end up with a pH of 1.78. And you can just do a quick check with yourself at that point, because you've taken a weak base, you've added excess acid, And so if you've got excess acid, you're expecting it to be at a low pH when you finish, which is what you found out when you did your calculation. So it's always worth doing a quick check at the end to make sure that you've got a low pH, which is what you were expecting. Okay, so you've now got to do a sketch graph here of the titration. And what you want is you need to know, well, you had your starting point. Well, what was the pH at the start of the titration? We calculated that way back at the beginning somewhere. Well, they told us, didn't they? I think. Yeah, there. That the pH starts at 11.9. So we've got a starting pH. And then we've just worked out, didn't we, an ending pH. So that's the one we just calculated just now. So we're going from a high pH, was it 11 point, was it over here? I think, was it 11.3 to begin with? Oh, 11.9, sorry, my mistake. So 11.9, and we ended at, what was it, 1.78. Okay, so we've got our start and our endpoints. And then you need to know that on your pH graphs, you've got a vertical section of the graph, which is called the equivalence point, when you've exactly neutralized all the base with just enough acid. Now, in the example that they gave us up here, we kind of added excess acid, didn't we? But if we wanted to add just enough acid to neutralize the base, then the equivalence point is actually not at 20 centimeters cubed, but if we had 15 centimeters cubed of acid, then we'd have exactly the right number of moles of acid to neutralize the piperidine. All right, so going back to our graph, you've got your equivalence point where all the base has just reacted with the acid at 15 centimeters cubed. So you're starting up here, you've got 7, 8, 9, 10, 11. So you're starting there, aren't you? And you're finishing down here at 1.78. So that's 6, 5, 4, 3, 2, 1. So you're finishing down there. And your equivalence point is there. Now, the only other thing that you need to know is the equivalence point above 7 or below 7? And that's the thing that you have to kind of work out. And the trick to doing that is knowing about something called salt hydrolysis, which doesn't seem to be particularly well covered in a lot of books. But at the equivalence point, you've got this, haven't you? You've got that. Yeah, my bad drawing again. You've got the piperidine, and it's got 2 hydrogen atoms there and the nitrogen atom there. And the point is that with salt hydrolysis, you've made a salt there, and hydrolysis is breaking things up with water. And you can have an equilibrium formed where you get bad habit drawing. You can get an equilibrium formed where you've got the base and you've formed H3O plus, and you know that that's acid. Okay, my writing's a bit bad. Let me try and just draw that a bit clearer if I can. Rubber. Can you guys see that okay? Okay. So at the equivalence point, you had this salt here, it was dissolved in water, and it sets up an equilibrium where you can take off one of the protons there and give it to water. And so water accepts the proton and you end up with some H3O plus in solution, which is acidic, so that you know that your equivalence point is Well, you know it's a 15 centimeters cubed, but you've just now worked out that the equivalence point is less than 7. So the equivalence point is going to be down here somewhere, isn't it? So this is going to really challenge my pen drawing ability. But you've got, here we go, you're adding acid, and as you get towards the equivalence point, you get to the vertical section of the graph, don't you, down there? And the equivalence point I'm trying to draw here is less than 7. So where it crosses the 15, it's less than 7. So that's, I would say there, that's my arrow. Trying to draw my arrow, that's my equivalence point at 15 centimeters cubed, and the equivalence point is less than 7. Good, so I think that's quite a tough one. You've got some data points, haven't you, from the calculations you've done. You can work out the equivalence point. The salt hydrolysis is a little bit tough, and also the graph that they've drawn is the opposite way round to all the graphs that you see in the books as well. So that doesn't help either. But we worked it out, so we're okay on that. Good, so you've done the hard work, and then you come down to an easier question at the end. Well, you've got to choose an indicator, haven't you, that is good for an equivalence point that is less than 7. So the indicator is going to be used about there, and you've got a fairly easy choice here. Well, the equivalence point is not, or the indicator is not going to be that one. It's not going to be that one, because they're a long way away from the equivalence point. And it's not going to be that one either, because that's still a long way from the equivalence point. The only option that's really there is an indicator that changes color around pH 3 or 4. And if we look back to the graph that we drew, well, what's that? We drew it about pH 5, didn't we? Maybe, so maybe that should be a little bit lower. But there's only one choice really in the indicator table that they gave us. So we're very confident that we've chosen the right one there. Good, all right, so working our way through. They're giving you another organic chemical here that you've probably not met before. Noradrenaline, neurotransmitter. You've got to name 3 functional groups on there. So I think fairly easy marks again. You've got one functional group here, haven't you? That's an easy one. That's amine. You've got another functional group here. Don't know why I get, and that's an alcohol. If you look carefully at the skeletal formula, you'd actually say that that's a secondary alcohol, wouldn't you? Because it's joined to a carbon here, which is joined to 2 other carbons. Whereas that, you could say that one at the end there is a primary amine. So you're just being a little bit more specific about these functional groups here. Now, these ones over here, of course, they look like alcohols, don't they? They look like the one that you circled over there. But because you've got an OH group connected to this one, which is an arene group in there, that's, well, you wouldn't really say that's an alcohol. That's more a phenol group that you've got there. You've actually got to just name 3 functional groups. So probably you're going to say primary amine, that's an easy one. Secondary alcohol, that's an easy one. And then you're just spotting that hydroxyl group off the edge of the arene is a phenol. So those are your 3 functional groups you're looking for there. Okay, now they're talking about making this this hormone. And the thing that you've got to spot, of course, because they're looking and seeing how good you are at reading these skeletal formulae, because you've got to be able to read those as well. And if you can look over here, you can see here's a carbon chain that has got, well, there's 2 carbons in there, isn't there, in that chain? Whereas here, just over here, you've got 1 carbon. So you know that somewhere in this box in the middle, this compound Z, you're adding an additional carbon, because on the right-hand side, you've got 2 carbons in a chain, and on the left-hand side, you've got a single carbon in the chain. So The reagent that you use for adding a carbon to a chain is a nucleophile, isn't it? Which is cyanide ion, yes? It's the nucleophile you can add to extend a carbon chain. And so the intermediate here is that group there with the hydroxide groups here and here. And then you've got over here, you've added this cyanide group. Okay, you've added one carbon, and the carbonyl group has become hydroxide. Sorry, an alcohol group there. All right, so you've got think of reagents for step 1 and step 2. This cyanide ion, it's extremely dangerous. Be very, very careful with cyanide. So you don't use, I mean, you don't use hydrogen cyanide. It's a gas. Breathe that in, and you won't be doing a lot more chemical synthesis after that. So you can't use that. And so instead of using hydrogen cyanide, you usually use hydrochloric acid and sodium cyanide, and that generates this cyanide ion for you. And there's a little glitch in the mark scheme there, because they say something, don't they? They say hydrogen cyanide, sodium cyanide, which is wrong. I think it's probably just a typing mistake in the mark scheme, because you don't use hydrogen cyanide. That's an extremely dangerous thing to go around using. So what they mean, of course, is HCl. I think there's just a typing error in the mark scheme that says HCN. So that's the reagents for step 1. And then in step 2, you've made this cyano group, or sorry, you've made this nitrile group there, and you want to end up, don't you, with an amine group over here. And to go from a nitrile, you guys are being extremely patient with my very bad writing. So you ended up with a nitrile group there, and the amine over here. And when you're going from a nitrile to an amine, that's a reduction, isn't it? And classic chemical for using to make a reduction is lithium aluminium hydride, or the other one that you see in books is a nickel catalyst and hydrogen gas. So you've got a choice there. Lithium aluminium hydride or nickel metal catalyst with hydrogen. And that's reducing, isn't it, the nitrile group to the secondary amine. Okay, so we're jumping around a bit here. We're going to need to look back at this molecule over here. And it says that that's reacting with bromine. And the thing that they're working on here is that if you just had a benzene molecule, that doesn't have a substitution reactions with benzene. And so there's something about the benzene ring here that makes it react with bromine, whereas a normal benzene ring on its own doesn't react with bromine. Okay, and you need to know that bromine is a kind of yellow-brown color. All right, and as the bromine gets used up, that yellow-brown color disappears. So going down, describe what you'd see. Well, what you'd see is that because the dihydroxybenzaldehyde is reacting with the benzene is yellow-brown or orange-brown. So orange-brown color is going to get used up, and you'd see the orange-brown color disappear, I suppose. Or the reaction might become colorless, and it starts off with the the orange-brown color from bromine. Now, bromine and benzene, they don't react together. There's something about this molecule that is allowing the benzene and the bromine to react with each other. And the reason is you've got these groups here, which are, they're called activating groups. Okay. And if you look in your data book, they actually give you which are the activating groups and which are the deactivating groups. So this is actually just something you can look up in your data book, because these activating groups mean that you'll activate, it's called the O position. So the short for ortho. And so you've got an O position there, which is the first one round relative to that phenolic group here. And you've got another ortho, which is relative to that phenolic group as well there. And because you're doing a substitution reaction, you're going to end up with this is the chemical you started with. It's got this phenolic group here, and that's going to activate and cause a substitution reaction to happen there. And you looked that up in your data book, and that was the ortho position. And you've got this other phenolic group here. It's going to activate that carbon, and you're going to get a substitution there at that ortho position. And nothing happens. Was it the carbo? What was on there? Was that an aldehyde? It was, wasn't it? Yes, it's an aldehyde. Okay, so that's just an H off there. So that's really, if you knew in your data book that they tell you which ones are activating and deactivating, and they tell you the positions, bang, you just got a couple of marks for looking something up in your data book. All right, now, again, I think that these are still quite easy marks. I've run out of the screen here, so let me, you've got, it's back to noradrenaline, isn't it? Okay, we're jumping around between the aldehyde and the noradrenaline. Now, the noradrenaline had the secondary alcohol and the primary amine, didn't it? Okay, good. That's the secondary alcohol. And this is the primary amine. All right, so we've got to work out what happens. And all you're looking at here is, sodium hydroxide is a base, yes? And so you need to know that these phenolic groups here, they're very, very slightly acidic. And so you just get a very simple reaction between a base and the acidic groups of a phenol. So you're going to end up with acid-base reaction. You're going to get that. And you could either say, well, why does it do that? Okay, so you've got that. You've got there. And actually, those are, you could draw that. You could, oh, no. Okay, delete. Where's delete? I don't know. Okay, back to the pen. Okay, you could have a negative charge there and a positive charge there. You've got, I'm just trying to draw an acid-base reaction here. It should be, so you've got negative. Okay, you've got that. Good. All right, so that's the first one. And then the next one down, of course, is you're then doing, you've got some acid. And this time you've got a spot, of course, that with noradrenaline, this end of the molecule, you see here, was acidic, wasn't it? Those two phenolic groups. And at this end of the molecule, you've got a secondary amine, which is basic. Scroll. Here we go. And so that means we look at the other end of the molecule this time. You've got the phenolic groups are unaffected. They're already acidic. They won't get affected by adding acid. And you're going to end up with NH3Cl. Or if you wanted to draw that as ionic, you've got that noradrenaline molecule. You've got your secondary alcohol. You've got that. Okay, so you're just doing, in the first part of the question over here, you had an acidic end of the molecule, reacted with the base. Here you had a basic end of the molecule, you reacted it with acid. Okay, I think those were probably quite easy questions. And this one, you just need to know that these are called acyl chlorides. And the thing about acyl chlorides is they're extremely reactive. And so when you add acyl chloride to this noradrenaline, you're going to get reactions all over the place. All right. So here's your noradrenaline. And this acyl chloride can actually react at all points. So those ones are going to become esters. Something weird happens there. Can't work out why that's happening. It's getting worse. Okay, so you're going to have one ester there, and you're going to have another ester there. So you've got two esters there. You're going to have another ester over here. Still getting some weird stuff going. Go away. So you're going to have that. And then you've made esters there, and you're going to make an amide over here. So I suppose that's quite a logical question, because up here, you looked at the acid end of the molecule, it reacted with a base. Here you looked at the basic end of the molecule, it reacted with an acid. And here you looked at a reactant that's extremely reactive, and so it reacted actually with every single one of the functional groups that was on there, except the arene ring in the middle there. Okay, so okay, you got 2 marks here. If you look back through there, you created 3 esters, didn't you? And 1 amide. So the 2 new functional groups you got there, you got 3 esters, and you got an amide. Pretty obvious what the 2 marks are for there. Good. All right. So, all right. Now, new question. Okay, we've got, so look, you really have to dig into these questions to work out the clues. You've got 2 isomers, you've given a molecular formula, and actually they're walking you through this nicely, aren't they? So both compounds react with sodium metal. Well, you need to know that's a reaction of an alcohol. The bromine water is being decolorized. We saw that something similar just now. You've got something that's orange or brown becoming colorless, and that means the functional group there is an alkene. So those 2 are quite easy, I think. The aqueous iodine, if you want to look that up, that's called the triiodomethane reaction. And this is a very specific test And you only get a positive test when you have, I'll try and draw this, that carbonyl joined to a methyl group, or you've got that methyl group joined to an alcohol. Okay, so it's a very, very specific test. When you add this solution of iodine and sodium hydroxide, you're going to get a yellow color only if you've got that carbonyl or that alcohol. Sorry, there's a carbon in there as well, that yellow color. Because in the reaction, the yellow color is produced by triiodomethane. That's why it's called the triiodomethane reaction. Okay, that's what's produced. And it's a test for either that carbonyl or that alcohol, just a carbon with a methyl group to one side. So we've got quite a few clues that there's an alcohol in this compound, there's an alkene, and there's this this kind of grouping there. A few other clues as well. And you end up with, if you put some candidate structures down, you end up with this. Oh, that. Let's try again. Remember, that was the thing we were testing for in the triiodomethane reaction just now. Okay, so that's given us our alcohol, our alkene, and the positive result from the triiodomethane reaction. And then we've got this one. Okay, so that one, what is that? That's a primary alcohol with an alkene, and this is a secondary alcohol with an alkene. All right, so we've got two structures, and it's asking us to talk about, the next question, stereoisomerism of V. That's the next question. And you've got a spot, haven't you, that in V, you've got this chiral carbon here. Okay. And so when you're drawing your stereoisomers, the type of stereoisomerism is optical isomerism, then you've got to think there's a mirror, and you can draw your two isomers and they're mirror images of each other. And so the chiral carbon is in the middle. You've got a CH3 group in the mirror, and then you've got an OH group in the mirror, and then you've got something coming out of the page. I'm just having a hydrogen atom coming out of the page, and then you've got going the other side of the page, you've got that. Okay, so our trick there was to spot, oops, that we had a chiral carbon, and then to draw this mirror down the middle and have those two as mirror images of each other. Good. I can see that I've run over time here. How are we doing for the question? We've got a ton of stuff left to do. I think, otherwise you guys are going to be here all night. I'm going to keep going, and if you guys wanted to follow up on Slack, then we can talk about things on Slack. But otherwise, I mean, this has got to be done to go up on for the video, but you know, it's a long session for you guys. So I think at this point, if you wanted to finish, you're welcome. I'll keep going. If you want to stay, you're welcome. But it has gone till 8:10. So. So I'm just going to keep talking here. Okay, so we did the mirror image there, 2 optical isomers each side of the mirror image. And for the neutral compound, that was when we had a cold dilute potassium manganate. That's a very weak oxidizing step. And so that just oxidizes up to a diol, which has the skeletal formula like this. Oh, whoops, wrong one. Okay, question about proteins. You could just look this up in your book, which is primary, secondary, and tertiary. That's pretty easy to do. Let me just fill it in. So you've got primary there. Sorry, that's secondary, isn't it, for the beta pleated sheet on the alpha helix. You've got tertiary, the folding of the protein chains, again there, and the linking of one amino acid to another. That's primary bonding. Okay, again, you look this up in your textbooks. You work out the complementary bonding for guanine and adenine. You look at the phosphate backbone, and you look at the type of sugar, deoxyribose. You can get through that quickly. In the DNA molecule, the 2 strands in the double helix held together by hydrogen bonding. And you need to say at that point that the hydrogen bonding is relatively weak, which means the strands can be separated during replication into individual strands of DNA. And you just need to look up the differences between RNA and DNA. RNA, of course, is ribonucleic acid, ribose nucleic acid, and DNA is deoxyribose nucleic acid. And then in RNA, the thymine that you had in DNA is replaced by the base uracil. So you can look all that up. And the last question then is a question about mass spectrometry. And you need to know, this is just something you have to remember, the formula for working out the number of bonds. You just need to look that up. You have to have 100 divided by 1.1 times the abundance of the M+1 peak divided by the abundance of the molecular ion. And if you work that out, that gives you an answer of 3.07, and that's approximately, isn't it? You've got 3 carbon atoms in this molecule G. Okay, you come down to the high-resolution proton NMR spectra for G. You've got hydrogen atoms in 3 environments. You can see them there, and you can look up those environments in the data table. And one of those environments is actually this one. It's carboxylic acid. And when you add the deuterium oxide, then you get proton exchange with the O there. So that becomes that. And that essentially makes sure that the peak that you had there in the proton NMR spectra disappears. So that's a way of confirming that you had an OH group there, because you can do proton exchange with a deuterium atom and you lose the peak. And then you have to do a few candidates, but eventually you're going to end up with This, if I do the fully displayed formula here, okay, and you can see there that you've got 3 hydrogen environments. You've got 1, 2, 3, which matches up with the NMR spectra. And here you've just got a hydrogen proton. So that's going to be a singlet, isn't it? And these ones here, they're going to be quartets, because you're getting split from the 3 hydrogens over here. And these are going to be triplets, because they're being split by the 2 hydrogens over here. So we're expecting 3 peaks, one of which is a singlet, one of which is a quartet, and one of which is a triplet. And if you scan back to here, you've got the singlet, which is there, you've got the quartet, which is there, and you've got the triplet, which is there. So we're pretty sure with 3 hydrogen environments that was correct. And then you have to draw an isomer, which would only give 2 peaks in the proton NMR spectrum. And if you draw another isomer like this, it's actually an ester, isn't it? Then you end up with 2 proton environments, don't you? You've got 1 proton environment there and another proton environment there. That's all there is in there. That's an ester. And then you can look up in the data book where you'd expect to get the peak from that one there and that one there. And actually, they're both going to be singlets, aren't they? Because there's no splitting that's happening there. Okay, we're still going. So, okay, 8. Okay, so it's saying here, well, you could watch out that a drug might be broken down by acid in the stomach. Well, if there's a peptide bond, of course, we know, in the stomach, all sorts of protein is being broken down, isn't it? So you can't possibly have any kind of peptide bond in the drug that you're making. And when a peptide is broken down in the presence of acid, we've met that a couple of times in this paper already, that is breaking a bond, hydrolysis. And then you need to look to see which one of these could be broken down by acid in the stomach. And if you look carefully, then we need to find the kind of bonds that could be broken in the stomach. And there, that's actually, so if I highlight that one there, that's a peptide bond, isn't it? Although actually, because it's not an amino acid that's being bonded here, I think it's better to call that an amide. So that can be broken down. You could also say that this one over here is an ester, and this one over here, that's an ester as well. Those can be broken down by hydrolysis as well. But following on from the point we had up here with peptide bonds, well, the amide bond here is identical to the peptide bond that you have between amino acids. And finally, it says, well, if you've got a hydrophobic drug and you need to protect that or you need to deliver that, well, the hydrophobic region is in here, isn't it? Because you have to operate on the principle that like dissolves like. And so a hydrophobic molecule, the drug, would dissolve in the oily region here of these carbon chains. So it would be the hydrophobic drug is being carried, or it's being dissolved into the oily region Q of that lysozyme, lipozyme. And then you've got to look at drugs A, B, and C and work out where they would be carried in that liposome. And you can see here they're absolutely covered in polar bonds, aren't they? You've got polar bond there, polar bond here. You've got polar bonds here, here, everywhere. I mean, all these molecules have got polar bonds everywhere. And so, you need to say at this point that the molecules up here contain many polar bonds, that can then dissolve in the area R here. Okay, I think we've reached the end now. Okay, so nano, well, 10 to the minus 9, isn't it? You've got milli is 10 to the minus 3, micro 10 to the minus 6, nano is 10 to the minus 9. And so these nano cages exist just below the micro level down to the nano level. So if milli is 10 to the minus 3 and micro is 10 to the minus 6, then the range for these nano molecules is just below the micro, 10 to the minus 7, all the way down to nano, which is 10 to the minus 9. And finally, you're using infrared radiation because infrared radiation just means that bonds stretch. But if you use more energetic radiation, use it at a higher frequency, then you can have bonds breaking, and that can lead to mutations. And that's the reason that infrared radiation is used, because the bonds in the chemicals are just stretching, no bonds are being broken. We don't have any mutations. Okay, all right, so that was a 2-hour paper from A2 level chemistry in 2014. It's been a long journey through the paper. If you have questions from that, then there'll be the Z Coach on the Slack channel, and it'll be great to catch up with you and your questions, anything about that paper on the Slack channel. Okay, thanks for listening, and yeah, good luck with your chemistry.